Good morning, everyone. Today, I will present my recent work in the field of aviation safety. Specifically, I'll be discussing the critical topic data preparation for precursor identification in unstable approach events in flight data. My name's Jay Yang, I'm PhD student from Beihang University. This critical topic is a crucial preliminary step in the process of identifying precursors to unstable approaches. So let's begin. In this work, our primary focus is on unstable approaches in aviation, an adverse event that occurs frequently. So, what is the unstable approach? Unstable approach refers to a situation in aviation where aircraft states are not properly stabilized as it approaches a specific altitude, typically around 1,000 feet high above touchdown. This lack of stability during the descending phase can lead to increased risks and potential safety issues. Let's direct our attention to the finger. It's quite remarkable why the approach and the landing phases collectively account for just 4% of the entire flight. They are associated with over 49% of adverse occurrence. So, we can see that the unstable approach is the main factor in most aviation accidents, like hard landings, loss of aircraft control, and so on. However, relying solely on the detection of unstable approaches may not be adequate to guarantee safety in aviation. It stimulates the demand for precursor identification, a proactive way to ensure safety in aviation. In this work, our purpose is to provide a data preparation pipeline for precursor-based event prediction, which offers standardized inputs and outputs. It's the preliminary work of precursor identification of unstable approach. So let's talk about the problems of data preparation. First, flight data is far high-dimensional. Also, the length of the time series data for recorders can vary significantly due to factors like flight plan, weather conditions, and pilot adjustment and so on. To address this variability and ensure consistent data inputs for event prediction modeling, we require equal length time model series for the future modeling. Therefore, in terms of the two main problems, we apply automatic filter section based on statistical method to achieve dimension reduction. Simple but efficient. Also, we implement a uniform dynamic time warping method to transfer inputs with variable lengths into equal lengths. It works well to address input variability. Next is the overview of data preparation pipeline. The pipeline consists of 4 steps. In the initial step, we segment the flight data into specific phases: precursor mining phase and the unstable approach detection phase. Second, we aim to identify and pinpoint unstable approach in UADP according to standard operation procedures and statistical analysis. Then, we need to use uniform DTW to transfer variable length time series into equal length ones. providing consistency in our data inputs. And in the fourth step, we can obtain lower dimensional filters. By doing all above the four steps, we can get standardized inputs and outputs from PMP and UADP separately. Here, as mentioned before, we define two crucial phases in data preparation process. First, precursor mining phase. The phase is dedicated to identifying potential precursors to unstable approaches. It plays a pivotal role in generating standardized inputs for our analysis. Second, unstable approach detection phase. In this phase, our focus is to detect or label unstable approach event. It serves as the basic for generating labeled output. And also, the selection of the attitude for two phases is carefully considered. For the PMP, we consider attitude range of 3000 to 1000 or 2 minutes duration deemed sufficient for precursor identification. And for the UADP, the selection of 1000 feet attitude is according to the distribution of the attitude at which unstable approach events occur. With our defined phases, we will process time series into our desired inputs and outputs. Exceedance rules are applied to detect unstable approaches, which serve as the labeled output in our analysis. These exceedance rules are primarily based on the reputable sources. However, it's important to note that some of these rules have been adjusted and fine-tuned based on statistical analysis of specific flight data in reality. So, the rules is represented in Table 1. It has 5 columns. I want to mention that the duration is defined the minimal time that at which a given event meet a rule. So therefore, when the table of the rules are available, an unstable approach could be detected when at least one of the rules is met. In the following, we will introduce the filter selection first. It has 3 steps. In step 1, we calculate the correlation metric between the variables, identifying highly correlated variable pairs, and remove one variable from each pair. As see the right figure is the removal procedure. Starting with a variable, like variable 1, we identify variables V2 and V3 that highly correlated with it. These highly correlated variables are removed and marked as visited. Moving forward, we skip the visited variables and continue the procedure with unvisited variables like V4 until all variables have been visited. So this is the removal strategy with correlation analysis in the step 1. And then we calculate FDR for all the filters to rank them. And then we choose a cumulative FDR threshold to obtain the optimal filter subset. In this section, the key idea of the uniform dynamic time warping compared to DTW is that every element in the reference signal aligns with an index in the query signal. So We search forward to find the nearly reference to obtain new indices A, as seen in the algorithm 2. This new indices A serve as a crucial role in completing the missing corresponding reference sequence in query signal. Need to mention that we use ratio attitude as reference variable for building alignment metric between reference and query in all variables. It is because the RA is relative to specific pilot task during flight phases. Then, one reference alignment metric is available, and we can apply it to other variables in this data set. Therefore, all the variables align uniformly. So we transfer the variable length time series into equal length ones. Let's talk about the experiments and analysis. The datasets are collected from EAFR of regional aircraft. We have 84 available flights, and each flight has over 3,000 variables sampled at 1 Hz. In the figure 2, we can see the variable length time series in the PMP. First, for future selection experiments, these results signify that the correlation-based future selection method successfully reduced the dimension of the dataset by approximately 32%. And the reduced dimensionality also can be roughly judged from the smaller areas of the red and the blue colors in the sub-figure B in figure 3 compared to the sub-figure A. And the figure 4 shows the number of select features varies as cumulative FDR changes. For example, when the threshold is set to 95%, nearly half of the variables are removed, leaving 349 variables in the selected feature subset. So, it verifies that simple and efficient method greatly reduce dimension by removing less informative features. Compared to DTW, UDTW brings the warped query in blue color closer to the reference signal in red color. It has enhanced the alignment accuracy. And also, we examine the local views of alignment metric between reference indices and query indices. UDTW ensures that every element in the reference signal is matched with the index in the query signal when we focused on the area enclosed by the red boxes. We also calculate the distance under the alignment metric of DTW and UDTW. First, UDTW marked as yellow line has smaller distance, indicating its improved alignment accuracy. In summary, the UDTW not only achieves equal length time series, but also achieves smaller distance under alignment metric. Now let's recap the key points and the findings we've discussed in the presentation. First, this paper introduced a data preparation pipeline for the precursor based on stable approach events prediction, and the pipeline generates standardized inputs and labeled outputs from PMP and UADP separately. And we used real flight record data to demonstrate the effectiveness of the data preparation method, providing standard inputs and outputs for modeling. This approach can also be extended to data preparation for other adverse events during takeoff and climb phases. In the future, fine-tuning is necessary in conjunction with the model process to achieve a lower dimensional and more comprehensive future representation. Thank you. Welcome questions.